Hello everyone, and welcome back to AP Biology with Mr. Jennings. Today we're actually going to get a little bit into content about Domain 0, and that is atoms. So we're going to really start this chemistry unit off here. Now, most of y'all have had chemistry before, majority of y'all should have, and we're mainly just going to review chemistry as a basics here. We're not going to go super complex. We're going to talk about some concepts that are a little bit more above just physical science and just that chemistry, but we're not going to go like AP chemistry, college chemistry level. We're going to keep it within the scope of the course. Now, chemistry is a very important part of biology. One joke is that biology is just an applied form of chemistry. And reality is you need to understand some basics here. So let's talk about atoms. Let's start with the most basic of all. Now, in biology, atoms are the smallest unit of matter that we care about. We don't really go into the subatomics too well, though you do need to understand them. Just a quick reminder. All atoms are made up of a nucleus with a proton and neutrons. And within that, outside of the nucleus is a particle known as the electron. And it's just the three basic subatomic particles here. I'm going to clear off this ink. Now, atoms are the smallest unit of matter, and there's roughly about 120 different elements, so that means there's roughly at least 120 different atoms. So there's, as we'll talk here in a minute, variations on the atoms of the same element. Now, biology primarily deals with only 4 key elements: carbon, hydrogen, oxygen, and nitrogen. These are the most abundant elements in our body, and they're the most important ones. Now, there's 10 minor elements. That is stuff like phosphorus. And there's 30 to 50 trace elements, which is stuff like magnesium and iron. But all these atoms and all these different elements make up the body in its very important forms. Now, one thing we talk about with atoms is how atoms interact with energy, and they do so in a very fascinating way. So what I want to draw here is the Bohr model of the atom. If you don't know, the Bohr model is a very simple atom. It's just a hydrogen atom. Hydrogen. It's got 1 proton, no neutrons, and electrons. So the Bohr model really operates on this idea of electron energy levels. And I'm doing this a little freehand here. And the idea is that atoms, whenever they absorb energy, so this here is absorb energy. So when atoms absorb energy, electrons, that's this symbol here, move up energy levels. They get excited. They start bouncing around. They're really hyper, really energetic, and they're just going to jump all over the place, and they're going to jump off the atom, or at least jump into a higher energy level. Conversely, they can sometimes get de-excited, because actually they want to go back to what we call a ground state. And that is called release of energy. Now, this energy is going to be released in a couple things. First off, you're going to often see what we call a photon. This is a little bit more advanced chemistry. It doesn't really deal with biology necessarily, but we'll see photons. But also we'll see what we call electromagnetic energy. And that could be the form of light, and it can be a form of infrared and heat. So we can actually see a lot of different things come off. While this doesn't seem at first to be a very big deal in biology, this is really important when we start talking about things like photosynthesis, cellular respiration, and really this thing we like to call the ETC. And much more than just that. But these are the 3 big ones that we will see probably first. So, energy interacts with atoms in all these fascinating ways, and this is something really cool. Now, this model here is Bohr model, just a reminder. This is very limited to just hydrogen, but the concept is the same for more complex atoms. Just this traditional, what we call planetary model, this idea of electrons orbiting, this is strictly limited and only really functional for hydrogen. Just want to make sure you understand that. This is not the Vesper model or anything. Now, when it comes to bonds, chemical bonds, you have to understand what bonding really is. So when 2 atoms get really close to each other, when 2 atoms get really close to each other, so we have, say, hydrogen and hydrogen, their electrons will sometimes overlap with one another, and that creates a possible chemical bond, how these interactions work. The first type of chemical bond we really talk about is ionic, and that's just a transfer of electrons. We'll use sodium chloride here, for example. Sodium has one electron to give. Chlorine has one electron it needs. So sodium is going to give its electron to chlorine. And in the process, sodium becomes positive, chlorine becomes negative. Bang, boom, you got sodium chloride. The positive is attracted to the negative. They can't escape each other for the most part. It's a very simple type of bonding. It's really sleek. But ultimately, it's very dull. There's not a lot of variety. Sodium chloride can only look like this. It cannot be like Na2Cl3. It doesn't exist. It's NaCl. And if you want to talk about that more, you've learned that in chemistry. You'll learn that a lot in AP chemistry. That's beyond the scope of this course. Now, covalent bonding is very interesting. This is when two atoms get close to each other and they share electrons. So let's take carbon, for instance. Carbon has four what we call valence electrons, these outer electrons. And let's say it brings along a friend like hydrogen. Hydrogen's got just one. Well, hydrogen is not going to transfer its electron. Complicated reasoning dealing with a thing called electronegativity, which we'll talk about here in a minute. It's instead going to share its electron. So it's going to look like the electron is with the carbon for a little bit, and it's also with the hydrogen. So we just circle these two, and they kind of share them. So hydrogen looks like it's happy, and carbon looks like it's happy. Well, I had to bring some frames to the party. Let's bring another carbon element, and let's say whatever, doesn't matter. Well, when they get this bonding, this creates a different infinite combination. So you can have a compound that looks like this. Pick a branch here. Or it can be almost the same chemically, looks about the same. But the branching happens in different locations. Now, admittedly, these two here, the subtle changes between the location of this on the second and third carbon doesn't really matter because of isomers, but really these here too. So, something really important to keep in mind. We'll talk more about that in a moment. See, not all atoms share their electrons equally. Some atoms love electrons a lot when they're in compound form. They are what we call electronegative. Now, electronegativity is going to be a really big factor in determining what type of chemical bonds you get. In terms of its ionic bond, a covalent bond, a polar covalent bond, all this stuff. That's, again, more of AP chemistry and more not AP biology, more chemistry and AP chemistry. Now, the general rule of thumb is, though, the more electronegative an atom is, the more likely it's going to pull an electron toward it in a chemical compound. And the general rule of that is even more so that if you looked at, say, the periodic table here, and you got typically the more electronegative atoms are everywhere up here except the noble gases. So stuff like fluorine, chlorine, oxygen, they're highly electronegative. They're really going to pull the electrons away from the other atoms in the element. Now, when you do this, you're going to actually create what's called a slightly positive one end of an atom and a slightly negative end. So let's take water, for instance. Now, water is the classic example of a polar compound. Now, oxygen here is highly electronegative, as mentioned before. So what that means is these electrons that are being shared between hydrogen and oxygen, they're going to spend more time with oxygen, leading to, we're going to use what's called a capital delta, a delta negative charge. So it's not really a negative, but it's just going to look a little bit more negative. And because this side is a little bit negative, you're going to get what's called a delta positive on these H's. And that's what's going to lead to a process called hydrogen bonding. Hydrogen bonding is very common in all biological molecules. It's very prevalent. It's one of the most important molecule bondings we're going to ever see. And that's basically where, let's say here, we got say another water. I'm not going to draw all those detailed lines. But water here is slightly negative on the oxygen side. Well, this hydrogen is slightly positive. We're going to do this thing here, little dashes. This is your hydrogen bonding, and they're going to kind of link together. Now, it's not a true chemical bond. It's what we call a van der Waals force. It's an intermolecular thing. But this type of bonding is really important in biology. We're going to talk more about this when we talk about water's properties, and also when we talk about organic molecules like proteins and DNA. Now, not all bonds are straight lines. Most bonds are actually in a variety of different angles, and now what determines those angles is really beyond the scope of this course, so do not concern yourself with it. All you need to really know is molecular shape and electron distributions and what's going to contribute to polarity. Because of water's unique shape, it's got this bend. We always draw it like this. Because of its unique shape, it's really positive. It seems really positive on one side and really negative on the other. It makes it a very polar compound. Now, when it comes to biology, shape is critical. Excuse me there. Shape is critical in biology. It is so important to understand that. Because this is how atoms interact with one another. So how do atoms and molecules know what they're actually dealing with? They don't have eyes like we do. So what do they have to do is interact with each other based on what we call specificity, which is the different types of shapes. So shapes really matter. And there's various compounds like that. For instance, your brain's normal hormones that help signal stuff is very similar to morphine. So there's a section of morphine that looks almost like your body's natural chemicals, and that's how morphine is able to bond to certain things and bonds to your serotonin receptors. And that's really where all this stuff comes into play. Because of these similar enough shapes, your body thinks, hey, this is something natural, we'll take it up. And holy goodness, this is a lot of stuff. And that's what happens. Now, we are really predicating on this idea of specificity. So you're going to hear me repeat a lot in this class. Form equals function. It's almost like a motto. The form of an object is going to determine its function. Structure equals function. Please, if you take anything away from this, it's that. Structure or form equals the function. You cannot have one without the other. Now, moving back on to chemistry here. Chemical reactions are what most of us really think of when we think chemistry. Chemical reactions are processes that break and form chemical bonds. That's all they do. Now, when they do that, you're going to get these things here where the new chemical compounds as a result, also known as the products, will have different properties than the elements that make them up. Those are the reactants. And this is what we call an emergent property. So these emergent properties are properties that we only see whenever the chemical reaction is taking place. It emerges from the new substance. And I like to use sodium chloride for an example. Sodium, if you put it in water in its elemental form, it tends to go boom. It doesn't like water a lot. It's very explosive. You can look those videos up on your own. Chlorine, it's a gas that can damage mucous membranes and cause death. It's kind of been in the news in some places. So chlorine gas is a very much toxic substance. Yet when you put them together, you get table salt. And it's delicious on our French fries. So we take two chemicals that do not seem to be very safe to put in our bodies, and we'll put them on a flat plate and eat them when they're combined chemically. That's an example of an emergent property. Sodium in its pure form is a metal, and it's very malleable, very soft, very explosive with water. Chlorine's a gas, and it's a very toxic, very reactive gas. So when you put them together, you get a solid crystalline structure that is ionic, and it is safe to eat. Actually, it's a necessary thing in life. That's really one of the great examples of an emergent property. They're not just limited to that, and they're not just as dramatic, but there's something to keep in mind. What you get at the end of a chemical reaction is not the same as what you had before, and it's not going to be very similar in some cases. Now, we don't just talk about chemistry as a whole, matter interactions, we also talk about nuclear chemistry in biology. Now, nuclear chemistry is not as crazy as it sounds, It's basically this idea that atoms of the same element, but can have different masses, are called isotopes. And that's usually due to neutrons. So if you want to know that somewhere, it's not really important to know that for this class. I do hit it pretty hard in my physical science kids, if you've had it before. And this is due to neutrons. Neutrons are a weighted subatomic particle. They don't have any charge. They really don't do anything for the chemistry, except for the nuclear chemistry. Because of this mass, some atoms are not stable. So some isotopes are not stable. This is what we lead to what we call radioactivity, and most of us think of radioactivity as a bad thing. And it's probably a good thing to think that. Now the reality is radioactivity can be harmful to cells for a variety of reasons, but also is very helpful in biology as a lab, and in biology labs as a radioactive marker for biological molecules. So we like to use it, say, if we want to make sure DNA is the mode of heredity. So we can actually put a radioactive element in DNA. So we put, radioactive phosphorus into DNA, and we can track it and see, hey, does this new cell here have a radioactive element or not? And if it does, that means it's probably the mode of inheritance. And that's the basis for how we determine that. It's just one example. So we use radioactive markers all the time. Now, let's conclude here. So when it comes to biology and chemistry, it's a match made in heaven. It is, like I said in the beginning of the video, biology is applied chemistry. Some of the stuff you learn in chemistry and how it interacts with the real world. And we're going to talk more about chemistry as we keep going through this little section here. I moved it up. It used to be after we did the evolution unit, and I moved up chemistry just a little bit ahead because students really lack some chemistry understanding for a variety of different reasons, it seems. So I want to make sure your kids understand chemistry, especially when we start talking about DNA during evolution. Now, for us, when we talk about this here, really the big takeaway for AP Biology is how energy interacts with atoms. That's not the only thing here, but that's really a big deal because when we talk about processes like cellular respiration, photosynthesis, and the ETC, but not just that, phosphorylation, cascades, and all that good stuff, lots of big words. Those all predicate on electron transfers and all that, and how energy is traveled. Now, the rest of the stuff does matter. We talked about radioactive markers and how bond shape determines function of the cell. So all these things do matter, and we kind of keep this as simple as we possibly can while not doing a disservice to the core material. So please understand that when it comes to chemistry, it is, again, not impossible, a little bit challenging, but I'm always here to have any service, and I'll answer any questions you may have regarding chemistry. If you have any questions about what determines polarity, you can ask your AP Chem teacher, or you can ask me and I can explain it a little bit after refreshing my mind because it's been a little while since I've done polarity. Again, it doesn't come up very often in chemistry and biology. It comes up a lot more in chemistry. Alright, next video you'll see here soon will likely be on water and what makes it very important, followed up by biomolecules and carbon. Those are pretty crazy compounds and ones we're going to take a little bit more time talking about. Well, thank you for watching. Much appreciated. Stay tuned.